In a batch digester, chips are fed into the top of the digester and cooking liquor is added. Once the digester is sealed, the digester is brought up to the desired temperature and the chips are allowed to cook for the prescribed length of time. At the end of batch cooking, the pressure is released through a blow valve at the bottom of the digester, and the cooked chips and spent liquor are discharged into a blow tank. The turbulent discharge flow disintegrates the cooked chips into fibrous pulp. A continuous digester produces pulp in a continuous stream. The wood chips are pre-steamed, then mixed with cooking liquor and transferred into the pressure vessel. Cooking occurs as the column of chips and liquor is heated to high temperature and slowly descends through the digester. When pulping is complete, hot spent liquor is removed through screens. It's replaced by cooler wash liquor, which is pumped upward from the bottom of the digester. The cooked material exits from the bottom of the digester through a special outlet device and is discharged into a blow tank or directly to a pulp washer. Spent cooking chemicals still with the pulp need to be separated for recovery and reuse. Pulp washing removes residual liquor as wash filtrate, and the filtrate is then sent to chemical recovery. In the recovery process, the filtrate is concentrated and then burned in the recovery boiler to produce high-pressure steam. We'll talk more about recovery in a few minutes. After washing, the unbleached pulp is usually screened to remove any material other than individual pulp fibers, uncooked pieces of wood, for example. Pulp screens use perforated barriers to allow acceptable fibers to pass while rejecting unwanted material. Then the pulp is thickened to about 10% consistency and sent to an intermediate storage tank. If the final paper product is unbleached, in other words brown-colored such as linerboard or grocery bags, the pulp is diluted and pumped from high-density storage to the paper mill. But many paper products, milk cartons, paper cups, and paper towels are examples, must be bright white, so the pulp has to be bleached from brown to white. Although bleachable-grade chemical pulping typically removes more than 90% of the original lignin, the small amount of remaining lignin is responsible for the brown color of unbleached pulp. Not surprisingly, it's usually called brown stock. Why not simply cook until all the lignin is gone? Because it doesn't work chemically. You have to change the chemistry to be able to dissolve the residual lignin. Bleaching is the way it's done. Originally, cloth rags were the raw material for paper, and bleaching the rags meant laying them in the sun to fade them and then boiling them in potash solutions. It took a long time. But way back in 1774, Carl Scheele discovered chlorine, which could be used to make hypochlorite, a powerful bleaching chemical. You probably have some hypochlorite in your laundry room at home. Liquid laundry bleach, for example, is a 6% solution of sodium hypochlorite. For many decades, chlorine and hypochlorite solutions were the most commonly used bleaching chemicals. Pulp bleaching is done in a continuous sequence of stages. Each stage uses a different chemistry and is usually separated from the next stage by washing. Here are some of the chemicals used in bleaching treatments and their shorthand designations. About 20 years ago, we discovered that bleaching with chlorine produces trace amounts of chlorinated dioxins and furans, which are toxic. Because of this environmental danger, many mills around the world no longer use elemental chlorine for bleaching. This is called elemental chlorine-free bleaching, or ECF. Some mills have even eliminated all chlorine-containing bleaching chemicals entirely, and this is called totally chlorine-free bleaching, or TCF. Greater use of oxygen, hydrogen peroxide, ozone, and enzymes has expanded the range of suitable bleaching reagents. But the favorite one by far is chlorine dioxide, a very selective chemical for removing residual lignin and making pulp bright white. And no, it doesn't generate dioxins. Here's a flow sheet of the overall recovery process. Hang on, because this part goes pretty quickly. In brown stock washing, black liquor is removed from the pulp and the black liquor is collected. Since it's been diluted with wash water, the weak black liquor is sent to the evaporators and concentrator, where most of the water content is removed. The resulting strong black liquor goes to the recovery boiler, where its organic content is burned as a fuel to generate high-pressure steam. Simultaneously, the inorganic chemicals from the black liquor, which fall to the bottom of the boiler, are recovered from the boiler as a molten stream, rather like lava flowing from a volcano. The steam generated in the recovery boiler is used to generate electricity in a turbo generator and is also reduced to medium and low pressure steam for heating the pulping and bleaching operations. The molten chemicals, called smelt, are dissolved in weak wash to form green liquor. The green liquor is clarified and sent to the slaker, where it is reacted with hydrated lime to recausticize it to fresh white liquor, which in turn is clarified to produce clean white liquor for use in the digester. The lime mud is washed and sent to the lime kiln for calcining, converting the lime mud back into lime. The filtrate from mud washing, called weak wash, goes to the dissolving tank receiving the smelt from the recovery boiler. Kraft recovery is a story of continuous loops of chemical reprocessing. If it looks a little complicated, well, it's because it is. But it's this process that makes the kraft pulping process viable. This